We're going to go ahead and talk about rational functions. A rational function is a polynomial divided by a polynomial. Remember, a polynomial has only positive whole number exponents, and you don't have any variables and roots and things like that. So if we would go ahead and graph this using our calculator, we would get a graph that looks something like this here. When you type this in, you'd want to put the whole denominator in parentheses. So you go 1 divided by open parentheses x minus 2. When you graph it, you get this here. And in this case, we have a vertical asymptote showing up at x equals 2. And that's because we cannot end up dividing by 0, and x being 2 causes the bottom to be 0. When we graph this one over here, we'd have to put the whole top in parentheses, put the whole bottom in parentheses. Notice it says we need to go to zoom decimal. So after you type this in, hit the top center button of zoom, then select zoom decimal. Then you need to go back to window, change your y min to 0, your y max to 6.2. When you do that, you should get a graph that looks like this here, which is a straight line, but you notice there's a hole in our graph right here. When we look at the second problem right here, we have differences of squares on the top. Differences of squares will factor into this here. You'll notice we have a common factor on the top and the bottom for this particular problem. When you have that common factor top and bottom, you end up having a hole in your graph. When you do not have a common factor top and bottom like the first one, you have a vertical asymptote at what causes the bottom to be 0. So when you're dealing with rational functions, you're going to either have a vertical asymptote showing up or a hole showing up at whatever causes the bottom to be 0. So looking at the first one, we have a vertical asymptote here at x equaling 2 because that's what causes the bottom to be 0. Whatever causes that common factor to be 0 is a hole. Now notice this one here, if you did cross these out, we would get an x plus 2, which you know is an equation of a line with a slope of 1 and a y-intercept of 2, and that's what it appears to be. So it's going to be a line except at x equals 2, because that's where we have our hole. So at x equals 2, we got to go up there and just put an open spot. Now, when you're dealing with vertical asymptotes, you're either going to come into your vertical asymptote and go up, or you're going to come into your vertical asymptote and go down. When we're looking at as x approaches a with a little negative exponent, that means as you approach a from the left, so just to the left of a, and this vertical line is a, just to the left of a, in this case it goes up. That means your function goes up towards positive infinity. This one here says as we approach a from the left, we come into a being to the left, it goes down forever. And that's a going down forever is for your function right here. There are times that you'll be looking at your vertical asymptotes and wondering what happens just to the right. That's as x approaches a, and a is our vertical line here, with a little plus as an exponent. That means what happens is you approach from the right-hand side. And in this case, as we approach from the right-hand side, we go up forever. So hence positive infinity for our function. Here when we come in from the right-hand side, we go down forever. So we have our negative infinity. So that's dealing with vertical asymptotes. We also need to look at horizontal asymptotes. And that's what happens to your graph as you go far to the right and far to the left on your graph. As you go far to the left, that's as x approaches negative infinity, you may level out at a particular height. And that's what we're saying here. Sometimes you level out that horizontal asymptote from below, like this one here. Sometimes you come and you level out at that horizontal asymptote from above. Then you also need to consider what happens as you go far to the right, as x gets really, really big. You could level out at that horizontal asymptote from below, or level out at that horizontal asymptote from above. Now with horizontal asymptotes, you can cross them Horizontal asymptotes only tell you what's going on as you go far to the right and far to the left on your graph. So we're looking at what happens when you put in a really big number for x. Does it level out at one particular height? So we're putting in big numbers for x, and that helps us find out those horizontal asymptotes. We'll start with the middle one here. When we put in a big number for x, you're essentially looking at what's the most influential on the top, what's the most influential on the bottom. Because if you're putting in 1,000,000 here, you'd have 1,000,000 then, or a 1 if it was 1,000,000 cubed. You'd have a 1 then with 18 zeros after it. A 7 with 6 zeros after isn't going to make much difference. So you'd look at most influential on the top and the bottom, and then you decide, well, let's go ahead and simplify that down. The x cubes dropped, and we get this. So we would have a horizontal asymptote for this particular function, and that would be y equals our number we got here of 3/5. When we look at the bottom one, once again, we go ahead and look at most influential over the most influential, because we're looking at only what happens as you go far to the right and far to the left when you put in really big numbers for x. We end up getting this here. That does simplify down to a 3 over a 5x. This is not just a number because we have a variable left. So then you got to think, what happens as x gets really, really big? Well, then it would be 3 over some huge number. 3 divided by something really huge is something close to 0. So we'd have a horizontal asymptote of y equals 0. When you look at the top one up here, we look influential on the bottom, and that's x. Influential on the top, that's our 3x cubed. We go ahead and we look at just those, and that simplifies down. And now we're looking at, once again, what happens when you put in a really big number. A really big number squared times 3 is something really, really big. So we have no horizontal asymptote in this case. We would end up having what we would refer to as an oblique asymptote. When x approaches infinity, you have either a horizontal asymptote or an oblique asymptote. If there is no horizontal asymptote, it ends up being oblique. And we'll talk about that a little bit later here. So to summarize that, when the degree of the top is less than the degree of the bottom, it's always y equals 0. When the degree of the top is greater than the degree of the bottom, and that would be like our last problem we did, there is no horizontal asymptote, but there would be an oblique asymptote. When the degree of the top and the bottom are the same, then it's just y equaling a number. And so then you got to take the leading coefficient here divided by the leading coefficient here, and that's your number that we would have. When you are graphing rational functions, I want you to follow these steps. I want you to go ahead and find the domain, and that's when you got to look at when the bottom is 0. Find your holes and vertical asymptotes, and that's also looking at the bottom being 0, but you're going to want to have the top and the bottom both factored. We'll then go ahead and find our y-intercept, and that's when x is equal to 0. We'll find our zeros where we cross the x-axis, and that's when y is equal to 0. Then we'll look to see if we have horizontal or oblique asymptotes. And what we have over here is the summary of what we had on the previous page. Then I'm going to want you to go ahead and plot all those on your axes. And then I want you to go ahead and graph it on your calculator and sketch it in from your calculator, going through all your zeros and your y-intercept with your vertical and horizontal asymptotes on there so you know what you get close to.